Okay, so this will be the first video in the solutions chapter, and first we have to discuss why solutions form in the first place. The solution is a mixture of two different substances or more, and they either dissolve in each other or they don't. And so one famous example is just a vinaigrette salad dressing. Water is more dense than oil, and so the oil floats on top, and they don't dissolve in each other, and so you have to shake it up actually to make tiny droplets of oil interspersed with the vinegar phase and try to pour it before it separates again. And so the principle behind this is has a little slogan, like dissolves like, and like means they're similar in chemical structure, which in turn determines their chemical properties. Okay, so basically nonpolar substances dissolve other nonpolar substances, polar substances dissolve other polar substances. Okay, and salts, since they're charged, and polar molecules, since they're partially charged, they dissolve in each other. Okay, so salts will not dissolve very well in nonpolar materials. Okay, so one example of nonpolar material is fat. So when we look at fat, fat is primarily just a CH2, 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 and a long backbone. And if it's a saturated fat, it's all single bonds. And so if it's in the form of an acid, and then has a carboxylic acid group. And this is a fatty acid. So most fatty acids have an even number of carbons, and so I've probably drawn an odd number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. There. Well, it doesn't really matter. We'll let that out. Okay. So this is a fatty acid. And so the CC bond is nonpolar, the CH bond is nonpolar, and so this is nonpolar. Now there is a little bit of an end out here. That is polar, but if it's a small part of the molecule, it still won't dissolve in a polar solvent like water. So you can't dissolve fatty acids in water. The other thing is that it can also hydrogen bond. It can hydrogen bond with water on that end only, either as an acceptor or as a donor. So remember, the donor is the molecule that has the covalent bond with the hydrogen that's donating to the hydrogen bond, and the acceptor is the electronegative element on the other molecule, which is a lone pair that accepts that hydrogen. So go back and review your Lewis structures, your properties, polar, nonpolar, intermolecular forces. Okay, so fat will just more or less stack with itself. Over here, we're going to draw water. So water is purely polar and has a dipole moment, which we're going to indicate off to the side with an arrow. And so this arrow has a little cross that is on the end with the partially positive charges. So the symbol for partially is delta here. Both hydrogens are partially positive. This one's partially negative because it's electronegative. And of course there's two lone pairs in here. So the water molecule, the electronic geometry is tetrahedral, sp3 hybridized, but the molecular geometry is bent since you can only see the hydrogens and oxygens when you look at the actual shape of the molecule. So water can hydrogen bond with itself, and so let's draw another hydrogen over here. Another water molecule. And the hydrogen bond is directed more or less at one of the two lone pairs on the oxygen. Okay, and this is very strong compared to the interaction between two fatty acids, which is more or less stacking on top of each other. So these compounds are solid at room temperature because the van der Waals forces, even though they're very weak in a small area, they're a lot of little small interactions adds up to a very strong attraction between these two molecules. So most fats, saturated fats, are solid at room temperature. Water, on the other hand, is very small. You'd normally expect it to be a gas since it's so small, but it's actually liquid because of these strong hydrogen bonds holding the liquid water together. Okay, so why don't water molecules and fat molecules dissolve? That's because in order to dissolve, get this great big molecule into a bunch of water, you have to break some hydrogen bonds. And that's going to be a high energy penalty, and you will not get that energy back from the intermolecular forces between this big nonpolar tail and the water. So that's the reason why nothing that's nonpolar will dissolve in water. Water says, hey, it's nothing personal. I don't hate you. I'd just rather be with myself. All right. And now, there is a way to dissolve fat in water, and that is to create compounds that have a charged end and a tail. So the way this works is to create something called soap. Soap is a carboxylate salt like sodium. Okay, so this end, which is charged, you have an anion and a cation. This is an anionic detergent because the thing that contains the greasy looking part is an anion. There are also detergents or surfactants. Those are substances which dissolve nonpolar molecules like fats in water, where the greasy part has a cation on the end and there's an anion. That would be called a cationic detergent. And then, of course, there are detergents which are neutral. So they might use a lot of hydrogen bonds to help dissolve in water. So when you look at the soap dissolves in water because of this part, and it dissolves the fat because of this part. And so it creates a tiny little structure called a micelle. So I'm going to draw the polar head group as a minus, and then the tail like that. And of course the counterions are out here floating around in the water. Okay. So the inside of this is nonpolar. Okay, so water's been excluded from the inside. And so that's where this thing dissolves. So the soap will be right at home inside here. Because it has nonpolar tail, it's interacting with all these nonpolar tails, and this whole thing is dissolving in water real well because it's got lots and lots of charges. That's how soaps and other surfactants work.